Uh, Thanks for giving me the opportunity. So this is totally a mathematical talk. So there is no physics and all, and it's fairly simple that even an undergraduate can understand this talk. So this is a very recent work jointly with Saikat and Navnath. So here I'll be talking about the graphs, wedge of graphs, and what are the topological, which is called independence complex of wedge of graph. So so a graph is basically a pair of vertex and edge. So, and for each edge, you have two vertex, and that two vertex need not be same, need not be distinct. Okay. For example, in this picture, like these are the vertex, the dotteds are the vertex, and these are like the edge, which corresponds to two distinct vertex, and this is a loop. This is a loop which corresponds to only one vertex, V1. So this is called a non-simple graph. So we, in the entire discussion, we will be considering a simple graph that does not contain any loop. Okay. So now what is wedge of graph? So this is not restricted to graphs. So this can be, the definition will be same for any topological space X and Y. So if you have two graphs G1 and G2, and then the wedge of two graphs is like you fix a point V1, a vertex, and V2, and just join these two or glue these two vertex. Okay, that will give you, so mathematically you take G1 union G2, so that's like you have one copy of G1 and one copy of G2, so that's a disjoint union, and you are quotienting with V1 and V2, so it means that you are joining the two vertex V1 and V2. So pictorially, if you have G1 and G2, and suppose that that's V1 and V2, so G1 with G2 is just joining along V1 and V2. So now, what are the independence complex? So for that, we need something called abstract simplicial complex. So it is a collection of subsets of n-point sets such that each of the singleton set Vi is in K, and if some set is there, then all its subset will also be there. So that's called abstract simplicial complex, and that singletons are called zero complex or zero simplex, and the edge, or let's say in the graph, so an edge is called one simplex, and if you fill it in the two-dimensional, then that's a two simplex, and if you are going to the three-dimensional, that's three simplex, and so on. So for example, if you have the 5 vertex, and then the abstract simplicial complex will contain this all, and if this sigma is in K, then from the second condition, all the edges, which is like joining V1 and V1, V2. So this is tau 1, and this is the earlier names. This is tau 1, tau 2, tau 3. This all will be in the complex in the K by the second condition. Okay, so now let's come to the final independence complex. So it says that if you have a finite simple graph with a vertex at V, then the independence complex is what? It's basically you consider all the independent sets of the graph. So what are the independent sets in the graph? So all the things which cannot be joined by a direct edge. Okay, so if there is no edge between two vertex, then that is called independent set. So for example, let me use the keyboard instead. Yeah, so for example, let's consider the P3, which is a graph with 3 vertex, and the P3 is it's called path graph with 3 vertex. So what are the independence complex? So what is the independence complex of P3? So here, so all the singletons will be there because it's an abstract simplicial complex, and the edge one, so the set 1, 3 will be there because that's the independent set, because there is no direct edge between 1 and 3. So this is independence complex of P3, but we are interested in the what is this topologically. Okay, so this is basically this blue curve is same as line, and we can just compress it to make a point, and those are topologically same. So it is basically same at 1 point, and finally the independence complex is same as 2 points. So that is called homotopically same. So we are interested to find out what is the homotopy type of the independence complex. So here the independence complex of P3 is 2 points, which we denote by S0. Okay. What about P4? So if you have 4 points, so it will be containing the 4 points, and the independent sets will be 1, 3, 1, 4, and 2, 4. So this is the independence complex of P4. Again, what is this? This is a line, and hence this is homotopically same as point, and therefore independence complex of this is a point. I'll discuss one more example in the path graph, that's P5. So here the 5 points will be there, and the one simplex or one will be 1, 3, 1, 5, 1, 4, and 2, 4, 2, 4, 2, 5, and finally 3, 5. And now you also have 1, 3, 5, because that is none of them are joined by an edge, so this whole will be there. So now what is the like topologically what is this equivalent to? So this filled part I can just shrink it to make a point, and hence that's nothing but a triangle. Okay, and what is this triangle equivalent to? This is nothing but a circle. So independence complex of P5 is same as circle. So in general, in order to find out the independence complex of path graph, we need something called a fold lemma, which says that if you have a graph with two distinct edges, two distinct vertex V and W, and let's say NV denotes the neighboring vertex of V, and if NV is contained in NW, then the independence complex of G minus W is same as the independence complex of G. And this is very important to find out the independence complex of paths and many other graphs. So like you can prove that independence complex of PM is either a sphere or a point. Okay. Now this is one type of graph. Let's come to the cycle graph. So if you have a 3 cycle, what is the independence complex of this? So here you have only 3 points, because all the edges are like not independent. So therefore this is like, so what is this? This is 3 points. But this we can see like 2 point and 2 point and just glue 1 point. So this is like I can see S0, which is 2 point, and another S0, which is 2 point, and gluing 1 point will give me the S0 wedge S0. So this is nothing but the S0 wedge S0. So I'm trying to write all the things in terms of the sphere. Okay. So now similarly C4 is the 4 points and the two edges will be there, and this is the independence complex. But and the 2 lines again you can contract to point, and therefore this is just 2 point set, and hence it's a S0. And finally the C5 will be, you have 5 point sets, and the independent sets will be 1, 3, 1, 4. Here 2, 4, 2, 5, and 3, 5. These are just independent sets, and this is the independence complex of C5. And what is this? This is topologically a circle, and therefore the independence complex is circle. And one can again show that, and this is not as simple as the path graph computation. So one can show that the independence complex of the cycle graph is either a sphere or a wedge of spheres. So this completes the preliminaries thing. So let's now talk about the wedge of the graphs. So firstly, I'll talking about the wedge of path graph. So if you have, and this result can be generalized for any collections of paths graph, so PM1, PM2, PMK. Okay, and now the wedge point here, I have not fixed the wedge point, so you can take any wedge point. So it says that if you consider the independence complex of PM wedge Pn, that's either a point or a sphere. Let's see with a fairly simple example. Let's say you have P3 and you have P2. So what are the possible wedges? So this is one possible wedge, and this is another possible wedge. Because if you go to the next wedge, that's the same as the previous one. So, and what is this? This is same as P4, and P4 independence complex we know. So let's see about what about this one. So if you see this, then I'll apply the fold lemma. So by considering V at the top point and W at this point, so recall that the fold lemma says that you can, if NV is contained in NW, then you can remove W and the independence complex remains same. So here I can remove W to get, sorry, I can remove W to get this figure. This is P3, and I know what is the independence complex of this. So in order to find out independence complex of wedge of paths, we'll apply the fold lemma repeatedly to get either a sphere or a point. Okay. Now what about cycles? Wedge cycle. So it says that it's either contractible, that's it's either a point or it's a wedge of spheres. Okay. So in order to show that, we need two concepts. One is called link and one is called deletion, and they are not concepts of graph, they are concepts of complexes. So the link is defined as like set of all sigma in K such that the sigma does not contains V and the sigma union V is in K. And the deletion is defined as the set of all sigma in K such that V is not in sigma. And from the definition, it is clear that the link is contained in the deletion. And the following lemma proves this lemma is useful in order to prove that independence complex of wedge of cycles. So it says that if link is contractible in deletion, so what do I mean by that? So if you have, let's say, sphere, and now you consider any circle on the sphere. So you can just drag that circle being on the sphere to make it a point. For example, so you have this, and if you consider any circle, because you can just make it smaller, smaller, smaller because you are on the sphere, and this will be a point. So we say that the circle is contractible on the sphere. And this says that the K is same as deletion, which the suspension of the link. So what is suspension? I'll just take 1 minute. So what is suspension? So it says that if you have any X, then the suspension is you just consider X cross identity, and you just collapse this and this. So you will be getting like picture like a double cone. So this is the suspension of X. So you take the suspension of the link and deletion and take the wedge. So this lemma is useful to compute the independence complex of wedge of cycles as well as the wedge of paths and cycles. So this also says that it's either a point or wedge of spheres. And yeah, this completes the, yeah, thanks.
Any questions?
Dependent complex for paths and cycles, but for undirected paths or undirected graphs, right?
Yes,
In
yes,
general,
yes, yes.
Okay. Can we do the same thing for the directed graphs also?
But directed graph, because you are working in the complexes. So it's like you have, let's say, if you are in the directed graph, then you have one, let's say 1 and 2 are the two vertex, and if you have one is like this and one is like this, suppose that this is directed graph. So then it won't be any like this is like a more general thing instead of directed graph, because in the directed graph, of course, yeah, there are some computation of the directed graphs, but not with the paths and cycles. With other directed graph, there are computations of the independence complex, but for the paths and cycles, directed graphs are not that much useful for the independence complex point of view. But yes, of course, you can do that.
Hello. Yeah. So I was just thinking these graphs, of course, appear in many different contexts. Now, like these kind of independence complexes, are they somehow natural objects to associate with graphs? First of all, and I was asking, and let me just maybe give one more context, which is that, let's say, for example, there are in Lie algebra and Lie groups, sometimes we classify using graphs.
Yes,
right?
yes, yes.
So various things that you're saying, for example, do they have a corresponding statement in Lie algebra. such
Yeah,
that-
that is what our next goal is, to find out, is there any correspondence between the Dynkin diagram and the independence complex? That is what we are trying right now. Like to find out a correspondence between the Lie group's Dynkin diagram and the independence complex, because the Dynkin diagram is same as the path graphs. So that is what we are right now, we are trying to do that.
Okay, okay. And the spheres, yeah, another thing that graphs are also useful for, are also, which is related to this Dynkin diagrams, is to classify singularities. And so
Yes,
on.
yes, yes.
So where you can think of products of spheres and how you contract them and so on.
Yes, yes.
So I was wondering whether these products of spheres that you're getting, do they say something about the singularities? But yeah.
Yeah, we haven't thought about the last one, but yeah, the previous one we have. And even if you triangulate a manifold, then you'll get a graph kind of thing. And right now we are trying to find out whether the independence complex of the triangulated thing has some relation with, let's say, some homotopy groups of pi m and all that. So that is what we are trying with all these things.
One last question. Okay, in that case, let's thank the speaker.